Hi everyone, Tina here, and today I'd like to talk about similar shapes. In this video, I want to talk about questions which involve looking at the lengths, areas, and volumes of shapes in 3D. With my students, I refer to this topic as LAV ratios because that describes the method that I'm going to show you now. I'll talk through some background information first to introduce the concept of LAV ratios, and then we'll work through some examples. First, let's start with a bit of background. If you consider two cubes in 3D. So we've got cube A and cube B. Cube B is just an enlargement of cube A. This means that the two cubes are similar, but A has a side length of 2 centimeters and B has a side length of 6 centimeters. So in a ratio, if we set this up to say A to B, and we think about just the lengths first, lengths of the sides, then A is 2 and B is 6. We can simplify that ratio to be 1 to 3, and that is our length ratio. Now, if we consider the surface area of one of the faces of each cube, then for the small cube, that surface area is going to be 2 times 2, so 4. And for the large cube, 6 times 6 gives 36. So again, if we're thinking about the area ratio, we've got 4 to 36. And if we simplify that, that's 1 to 9. So far, I'm just writing down a bunch of ratios on some information that we have about these two cubes. Last piece of information I want to consider is the volumes of each of these cubes. For the small cube A, volume is going to be 2 times 2 times 2, so 8 centimeters cubed. And for the big cube B, it's going to be 6 times 6 times 6, so 216. If we simplify that ratio, it turns out to be 1 to 27. Now, if you have a look more closely at these ratios, if I highlight the length ratio, simplified version was 1 to 3. Comparing that with the area ratio of 1 to 9, do you notice that we've actually just squared the length ratio? So if length ratio is labeled as x, then the area ratio can be x squared. And similarly, there's something interesting going on with volume. That volume ratio is actually just the length ratio cubed. So again, if length is labeled as x, then volume is labeled as x cubed. This forms the template in the LAV ratios method that we're going to use today. Let's work through some examples so you can see this method and template used in practice. Example 1, we've got two shapes here, A and B, which are mathematically similar, again, which just means one is an enlargement of the other. We're told some information in the text and also on the diagram. So the base of shape A is a circle with radius 4, and the base of shape B is also a circle, but the radius is 8 this time. So straight away, I can see that this is going to be about LAV ratios or similar shapes in 3D. So I'm going to go ahead and write my LAV down the side, x squared, x cubed as a reminder of the method. And then at the top, a reference to the two shapes, so A to B. Looking at the information we're given in this question, we're given information first of all about the radii. So that is in reference to lengths. Let's write that next to L, 4 to 8. I always like to simplify the ratio where I can, so that simplifies to 1 to 2. We're then told that the surface area of shape A is 80, and we've got to work out the surface area of shape B. If we look at the area ratio part of our template, first thing we're going to want to do is square the length ratio. So where we had 1 to 2, let's square both of those numbers, and that would give 1 to 4. And that is our area ratio that we can then follow. So if we stick the 80 underneath the 1, because that corresponds to shape A, now all we have to do is multiply 80 by 4 to get the area of shape B. And the answer is just 320 centimeters squared. Part B then says that the volume of shape B is 600, and we've got to work out the volume of shape A. So again, looking at our template, there's nothing next to the V, which is a reminder that we haven't actually got that ratio yet. So let's take our length ratio of 1 to 2 and cube both numbers this time to get 1 to 8. And then we're just filling in the information that they're giving us in the question. So 600 would go under the 8 because that's the volume of B. And then to work out what the volume of A would be, just going to do 600 divided by 8, which gives 75. So 75 centimeters cubed is the volume of A. Now, there are lots of different ways of doing questions like this, but I really do prefer this method of LAV ratios because I think it's the clearest and easiest way to do it. But let's do a couple more examples so you can see as well. Example 2, two mathematically similar cylinders this time. And we're told that the length of A is 4 centimeters and the length of B is 6 centimeters. We're told the volume of A is 80 centimeters cubed, and our job is to work out the volume of cylinder B. This is the kind of question where we can use the LAV ratios method. Let's go ahead and write down our template. LAV on the side, x x squared x cubed, and then a reference to the two shapes, so A and B at the top. Now we can fill in what we know. So we know that the length of A is 4 and the length of B is 6. Again, my recommendation would be to simplify the ratios as you go along. So that simplifies to 2 to 3. And then thinking about what we want to know in this case, we're not actually interested in the area at all. So you can skip that part, leave that part of the template blank, and just go down to the volume part. So if length is 2 to 3, we need to cube both of those to get the volume ratio. So let's do that, and we would get 8 to 27. Now we're told the volume of cylinder A is 80, so that goes under there. And all we need to do is work out the volume of cylinder B, so the other side of that ratio, which would be 270. And that's it. Last example, this time we've got two cones that are mathematically similar. So we know that the total surface area of cone P is 24 centimeters squared and the total surface area of cone Q is 96 centimeters squared. We're also told the height of cone P is 4 and we need to work out the height of Q. Now, this example is good because it's going to show us that actually we can start anywhere in the template and work backwards. So this time it's not actually A and B, it's P and Q. So I'm just going to put P and Q at the top as a reference. And we're told information firstly about the area. So yeah, we can start wherever we like in the template. And in this case, we probably want to start with the area. So 24 can go there and 96 can go there. Always simplifying if you can. So that simplifies to 1 to 4. Now that we know that, we can work backwards to find the length ratio. So if A represents x squared, then to get the length ratio L, we just need to square root both of those numbers. And that would be 1 to 2. We then just fill in what we have and then work out what we want to know. So we're told that the height of cone P is 4, so that can go there. And now hopefully you can see that the height of cone Q is just going to be 8 centimeters. After that, in part B, we're told that the volume of cone P is 12, but we haven't got anything to do with our volume ratio yet. So let's go ahead and work that out by cubing the length ratio. So cubing 1, cubing 2 gives 1 to 8. And then we can put the 12 under the 1 for P, and then just work out the volume of Q by timesing 12 by 8, which gives 96. And that's the answer. The volume of cone Q is just 96 centimeters cubed, and we're done. That's it for now. If you found this video useful, please do remember to like, comment, and subscribe to my channel if you haven't already. And please do share this with anyone else that you think might find it helpful. Thanks, and see you next time.